Hello everyone, welcome back. Today we will discuss beta-migratory insertion. We started discussing in the last class. Beta-migratory insertion was first reported in 1962. Since then it has revolutionized, or it has evolved in a way perhaps no other reaction has been evolved in organometallic chemistry in that fashion. Quite a number of reactions like hydroformylation, hydrogenation and Ziegler-Natta polymerization rely on beta-migratory insertion as the key step. Let us look back at the beta-migratory insertion, and today we will discuss little more in depth about beta-migratory insertion. So, as we tried to discuss in the last class, beta-migratory insertion involve this metal with a hydride and olefin coordinated, for example, and then we will get a metal alkane species. As you can see, the H is at the beta position. Okay. Now, this reaction can be of different type. Let me give you one example. You have a metal hydride with two ligand and a chloride. This ligand could be, let us say, triethyl phosphine, and under 40 atmosphere pressure you have this ethylene reacted 40 atmosphere pressure. You will get the product that is over there. It could be with platinum as the metal, right. Of course, first example of any metal hydride species getting into the metal hydride and olefin interaction, and thereby this beta-migratory insertion with the hydride was first reported in 1962, but first metal alkyl insertion at the beta position was reported in 1982. Of course, as you can imagine, we can draw the exactly similar thing for this metal alkyl one, where metal R is coordinated with the olefin. Overall you get metal alkyl R intermediate, where R is now at the beta position. So, this is the beta position, R is involved. So, this was first reported in 1982. Of course, then we can have quite a lot of discussion on this, but most importantly we need to understand when you have a terminally substituted olefin, where the beta position is going to be, which beta position the alkyl group, let us say for example, will terminate, whether it is the less substituted position or the more substituted position the alkyl group will go, because both the more or less substituted one you can call as the beta position. It actually depends on where the substrate or the H or R is getting migrated. Let us try to look at one of the example perhaps which can determine which center, whether the more substituted center of the olefin or less substituted carbon center of the olefin will have the migratory group. For explaining this, we have one of the very important example. This was reported with cyclopentadienyl as a supporting ligand with lutetium and with a methyl. So, of course, you have an alkyl group in there. You want to react it with this propene, let us say for example. Now, let me draw the product. Two products are possible. One of them could be this one, for example. Then you have alpha beta, of course beta migratory insertion product. The other one would be your CP star, the same compound, but here you have the methyl group at, let us say, over there. Now, in this case again, this is the alpha one, this is the beta one. So, it all depends how the olefin is oriented and where the alkyl group is getting migrated. Now, if you look at these two products, it's both of them are beta migratory insertion product. The first one, as you have seen, the R group, that is alkyl here, methyl to be particular in this case, has been transferred at the beta position. Of course, both the products are beta product, but it is having the center which is more substituted one, the carbon center having the more substituted one possessing the methyl group. In the other one, the second product that we have drawn is the one where the methyl group is present at the less substituted position of the olefin, but again that is also a beta migratory insertion product. Both of them being the beta migratory insertion product, which one is going to be more in amount, or the major product, or let us say exclusive product in a lot of cases, which one is going to be the one. If you look at the first product is the one where the the overall metal alkyl species that getting generated is having least steric hindrance at the metal carbon center. So, the alpha carbon center which is attached with the metal is having least steric demand in the first product. In the second product, you can see the alpha carbon center is housing methyl. Let us go back and look at the product again. We have the alpha carbon center. Okay. Alpha carbon center is least substituted or least sterically demanding, but over here you see the alpha one is more sterically demanding. Now, if you look back, therefore, actually the first one, the first product which is having the metal carbon center least sterically demanding is the one that going to be preferred. The first product is going to be preferred. Of course, in some cases you can get nearly exclusive product formation. This is mainly due to the fact that metal alkyl species are stable if the alpha carbon center is less sterically demanding. That makes sense, right? So, let us try to write down that fact. So, we have generally, of course, there could be different other factors involved. Generally, we have primary metal carbon, that means primary metal carbon complexes or metal alkyl complexes is preferred over secondary metal carbon complexes. So, that is in terms of the stability. This is the secondary one, this is the primary one. Primary, secondary, primary is more preferred. Of course, that trend will follow primary, secondary, tertiary. As you can see, more and more steric demand is happening, and therefore we will get less and less product formation. Now, as we try to discuss whether the hydride migration or alkyl migration, which one, if you have a competitive situation, which one is more likely, which one is facile, let us say. Now, that is a very tricky experiment to do. You have to make sure that everything is remained as constant as possible, as similar as possible, then only you will be able to make some judgment about whether hydride transfer is faster or alkyl transfer is faster, right. That is literally a tricky experiment to do, but of course, scientist has got around this problem, and they have come up with a really beautiful design of the experiment. Let me try to discuss that particular one with you. So, that will be on migratory aptitude, which group, that is hydride or alkyl, migrates faster when there is a competitive situation, or how will you prove that one is faster over the other? Are they working in a similar fashion, exactly same rate? Of course, you can imagine that they are not, but let us try to see the example, one example with this. So, the migratory aptitude. So, in order to probe this mechanism, of course, it is going to be little tricky out there, but I think scientists are very clever in designing this experiment, this rhodium complex. Okay. Now, let me write down the experiment and I will try to explain along with it. So, this is the rhodium complex with the olefin coordinated. Now, you have a protonation. Okay. Of course, proton will bind with the metal center, and overall you will have Cp star L rhodium and olefin coordination along with the hydride species in there, and this is a plus complex, right. Now of course from this intermediate you can expect that your product formation will be going on, and in this case the product would be the one where rhodium is having the alkyl group. So once again alpha beta, at the beta position this hydride is getting migrated, right. So again this will be at complex. Now if you do the electron count, I should have done that initially, this should be 18 electron count, and this ligand could be this trimethoxyphosphine, and Cp star as you know is C5Me5, right. So this is a beta migratory insertion where you have the hydride transferring to the beta position of this olefin. So alpha beta position hydride is getting transferred. Again this is an 18 electron complex and so on. Now once you have this olefin excess, okay, now this reaction can be done at minus 30 degrees C. This is important to note, this reaction can be done at minus 30 degrees C. Now delta G for this reaction is going to be nearly approximately 12 kcal per mole, So this is 12 kcal per mole, very nice. But if you do this reaction in presence of excess, excess olefin, what you could expect that, let's say you are doing further slowing down the reaction, or further doing the reaction at a lower temperature where you will be able to bind with the another excess equivalent of olefin, then the product as you can imagine will be, so after minus 30 degrees C you cool down faster to minus 80 degrees C, the product you are going to expect or you are going to get is the one where you have the olefin coordinated with this alkyl intermediate. Now of course from there on, if you try to heat it at room temperature, the reaction will be then Cp star L rhodium, and you are going to get this beta migratory insertion, this whole group become alkyl, then this is alpha beta and the whole group migrates. So what we have seen so far in this reaction, we have started with a rhodium complex. We have started with a rhodium complex that has olefin coordination in it. We tried to do the reaction first at minus 30 degrees C, which will ensure that olefin will coordinate with the rhodium, okay, and also the protonation will occur. So the protonation will give you the intermediate where beta migratory insertion is possible. Now that intermediate, if you try to do the reaction further, it will be, of course the reaction will go on further, you will get the beta migratory insertion of the hydride, and the delta G double dagger for this reaction is found out to be something like 12 kcal per mole, right, at minus 30 degrees C. Now from that intermediate at minus 30 degrees C, which is a metal alkyl intermediate, if you further cool down the reaction mixture, and if you are doing the reaction, let's say you are doing the reaction in presence of excess olefin, what will happen that the metal alkyl species will have coordination with olefin. So olefin coordinated metal alkyl species will be generated at minus 80 degrees C. Subsequently, if you heat that up, okay, at room temperature, then so 23 degrees centigrade, let's say for example is the room temperature, that at room temperature you will be able to get that alkyl group, the whole alkyl group, ethyl group to be particular, migrating into the another olefin that is coordinated at minus 80 degrees C, giving rise to the product. In this particular case it will be a long chain product like a butyl intermediate, metal butyl intermediate you will be able to get. Now let us look at the scheme once again. So we have this step, of course this is a beta migratory insertion, this is the beta position. Now this is also a beta migratory insertion, as you see that at the beta position this whole alkyl group is getting transferred. Now this reaction delta G for this reaction is going to be something like 22 kcal per mole. So, if you look at what we are now having is a very interesting situation where we can follow the energy profile or energy demand for the alkyl group insertion into the olefin, ethyl to be particular, ethyl group insertion into the olefin. Everything else remains exactly same. Over here we have this hydride migrating at the beta position. So, if you compare and try to look at this step and the step over here, the last step, of course, from here on you can further carry on next reaction if you want, but of course, you have to again cool it down, bind with the olefin, you can do further reaction. If you do not do it further, let us say you stop it over here. So, you have an intermediate, you have a reaction where the hydride can be transferring into the beta position of the olefin. Same way in this olefin exactly everything remains same on the in place of hydride you have the alkyl group. Now alkyl group is migrating at the beta position of it. So, it is, I think it is a very good experiment. We have now then a clear cut example that can compare these two cases. Right, we have a very clear cut example that can compare these two cases. One is hydride migration, beta migratory insertion of an hydride, another is beta migratory insertion of an alkyl, in this particular case ethyl. Now, as you have seen, the reaction required for the alkyl group, the reaction required 23 degrees C, whereas at low temperature you can do the hydride migration. The energy difference, now if you look at the energy difference, let us try to look at this energy difference little bit closely. So, the 22 kcal per mole and 12 kcal per mole. Overall then what we have a situation is, it is going to be the energy difference between these two steps is 22 minus 12 kcal per mole. Of course, hydride transfer is faster, alkyl or in this case ethyl transfer is slower, which is equivalent to 10 kcal per mole, and then that actually what it adds up is nearly 10 to the power 7 times faster. So, hydride migration is 10 to the power 7 times faster. That is quite interesting, right? One would not imagine that value would be so much, right? Now, of course, this is happening because after protonation, the first form intermediate, as you have seen, after protonation it is positively charged. So, ethylene can bind and form the adduct very efficiently. In the first case, as you have seen, after at minus 30 degrees C, you have one ethylene binding. At lower temperature, you have further ethylene binding, another ethylene binding. This is possible only because the metal center is becoming more and more positive, and their olefin coordination becomes more and more feasible. So, let us try to write down the equation very clearly. So, you have H migration versus R migration, and that is going to be your nearly 10 to the power 7 times. In general, if you like to put in general, we will have KH is greater than K alkyl. Okay. So, that is the in general formula. Now, I hope this is a very simple example and you have realized that this example can give you an idea hydride migration versus alkyl migration, and of course, in general it is you cannot in chemistry usually we do not want to generalize too much, but that is the usual found trend, but one may not take it for granted all the time, right. You have to see the situation. If under the same situation, yes, you can perhaps call that hydride migration is faster over the alkyl migration. Okay. So, I guess so far we have discussed alpha migratory insertion and beta migratory insertion. Next Of course, you have seen the alpha and beta migratory insertion in a number of cases. Next, we would like to start with the beta elimination, right. Now, of course, beta elimination is just opposite of beta migratory insertion, right. We have seen oxidative addition, reductive elimination, alpha migratory elimination, alpha migratory insertion and elimination, beta migratory insertion and beta elimination. We will now see the beta elimination. Of course, we will try to discuss with one example as always, and try to discuss further if today time permits. Let us see. So, beta elimination in general, that is what it is called, beta elimination. Now, of course, the first step is it is microscopic reverse of beta migratory insertion, that goes beyond saying at this point, and it is a concerted 4-center syn elimination, concerted 4-center, okay, that I think you guys will be able to find out by now, syn elimination. Now, let me give you one example. It will be just opposite to the beta migratory insertion that we were trying to discuss today. Let us say the product in this case particularly, let us say this one you try to pick up, and as you know, it is going to be a reversible reaction, 4-center reaction you can show very nicely over here, and that will give you the intermediate where this is nicely drawn 4-center intermediate. Of course, sorry, this should be of course dotted line here, and you have of course the other hydride or other species. Finally, you are going to get the product where metal olefin and hydride is coordinated. If this is the n electron complex, okay, of course this should be no doubt n plus 2 electron complex, right. Now, so this is a generic example, as you can see. Previously we have seen the generic example of beta migratory insertion. This is the opposite of beta migratory insertion, that is the beta elimination. We tried to give the example where we have hydride elimination, right, beta hydride elimination. Now, of course, it is possible to have beta alkyl elimination, just like insertion. Elimination is also possible, but it is extremely rare. We do not see that often, but of course under special condition special cases you can still promote beta alkyl elimination, but the most common one is the one that we see almost routinely, and that is the beta hydride elimination. Sometimes this step could be a nuisance. It can be problematic for a desired reaction, let us say where you do not want beta hydride elimination to be occurring, and it ends up happening. So, that potentially causes the problem for the desired other product formation, more valuable product formation. We hopefully will be able to discuss those little later.